Hi. Uh, well, first, let me thank the organizers for the invitation to come to this conference. You know, the first day was, of course, very intensive and very nice. And I'm quite sure that the other days will be like that. So even though maybe many of us could be exhausted, I think we're all happy to have listened to the beautiful talks we had before. And I have this responsibility of not delaying too much your dinner. So, and the chair of the session has already put pressure on me. He will go down and stay at the center because I cannot look at him. And I thought that would be a very good excuse for continuing my talk. But of course, he knows about that, so he'll, he'll, he'll go there when there are 5 minutes left for my talk. So uh, I'm going to tell about quantum sensing beyond the classical of limits of precision. Of course, that has to do with many of the talks presented in this session. I don't think I need to tell you about this. You know, I did not have a conversation with Philippe beforehand, so we just this first slide is about things he mentioned in his talk. We now have magnetic sensors for brain imaging that with a precision that goes down to 10 to the minus 11 g, the gravitational acceleration. We have gyrometers, which are small equipments, few cubic centimeters, with a precision which is 1,000 times the precision of optical gyroscopes, and accelerometers, like Philippe has told you, which, if perfected, they would imply no need of GPS for navigation, which, of course, for submarines is important, but also some regions of the Earth that do not have a GPS, that would be nice also. Of course, as mentioned by him, gravimeters can be used for oil prospecting, water prospecting, and even for satellite-based gravimetry, which measures the small changes in the Earth's water mass, which affect the mass distribution and therefore gravity, and that can be used for climate monitoring. So it's amazing, and I do believe that this field of quantum metrology or quantum sensing is one of the most promising fields of quantum information. And I should say that nowadays, not even promising. You know, some devices have already been built, and they are being sold actually. Now, people have told you about that. I think I don't have to go into detail. That's a very nice example of the use of squeezing for exploring the early universe. Now, the figure I'm showing you was obtained from the Livingstone interferometer, and that corresponds to the third observing run. Now they are planning the fourth observing run, actually started in May of this year. And you see that each run has enlarged the portion of the universe which is being explored. One parsec is 3.26 light years. So this keeps increasing. And the fifth observing run should cover that last line you see there to 40 to 325 megaparsecs. So we're really exploring more and more the early universe. And that's very interesting. In this curve, the green portion is due to squeezing. Of course, as was mentioned already here, squeezing will be efficient for higher frequencies. For low frequencies, it is not. But now you can change the phase of the squeezing. So you can also control this low frequency region. So that's an amazing application for the good of our knowledge about the universe, about ourselves, about the origin of the universe. So it's a very interesting and important development. But still, you know, we have questions to be answered, and these questions apply, I think, to many problems and many demonstrations that have been shown today. So first, you know, what is the proper metric to analyze the precision in the estimation of parameters? Second, are there fundamental limits? Is quantum mechanics helpful in reaching a better precision? And third, how to cope with the deleterious effects of noise, which is always present, of course. How does it affect, affect the precision of estimation? So the way to answer this question is very much related to the problem of distinguishing two probability distributions. So that's the question we want to answer. How much does the outcome probability distribution of an experiment change by a change of a parameter which is being measured? Now, we can distinguish, or we can apply a measure of that by using the fidelity between two distributions. And that's the definition of fidelity, which you see there. You have the two probability distributions corresponding to two different values of the parameter. Of course, if x is equal to x prime in that first equation, you get that fidelity is equal to 1. Now, if x prime is x is equal to x plus dx, so it's a small variation of the parameter, you can expand the fidelity in terms of dx, and you find an expression like that. You see, there is the identity, and then there is a term which is proportional to the square of this difference of the parameter, and the function which is multiplying the dx square is given below, and it's actually the Fisher information. Okay, so the Fisher information you see is measuring, if you want, since it's multiplying the x squared, it's associated to the speed of change of the fidelity when the parameter changes a little bit. Okay. Now, and this should be associated to the uncertainty in the estimation of the parameter, because if for the same dx you have a better, larger decrease of the fidelity, that means that you'll be able to assess the value of the parameter with more precision. So this shows immediately the relation between the speed of change in this function, which is called Fisher information, and the precision of estimation of x. In fact, this was mathematized and demonstrated by Kramer, Rao, and then Fisher, who showed that the uncertainty in the estimation of x is given by this expression, is bounded below by this fraction, which is 1 over the square root of the Fisher information times the number of repetitions of the experiment. And delta x here is just the standard deviation of the parameter with respect to the average value of the parameter. So Fisher showed that this relation, which is an inequality, can actually be saturated when the number of repetitions goes to infinity under some assumptions. Okay? So this is the metric, actually, for estimation of parameter that tells you how to determine the best possible uncertainty. Now, what about the quantum Fisher information? Again, we can define the quantum Fisher information as a measure of the distinguishability of the parameter-dependent probe states psi x and psi x plus dx. So this figure that you see there shows the development of a probe that is sent through the system, which has a parameter that you want to estimate, and then you measure the probe afterwards, assuming that the probe depends on this parameter, and from the measurement you can estimate the value of the parameter. Now again, we can introduce a metric for that by the fidelity between the two states of the probe, psi of x and psi of x plus dx, small change of the parameter, and that again, if we expand in terms of dx, you'll find that the correction to 1 is proportional to dx squared, and the function which is in front of that is the quantum Fisher information. So the quantum Fisher information, again, is a metric for the speed of variation of the scalar product between two states, of the fidelity between the two states of the probe when the parameter changes a little bit. Now just compare this quantum expression with the classical expression I mentioned before. Now in terms of the probability distributions, I have wave functions, of course. But you see, one corresponds to the other. And one can show that this quantum Fisher information corresponds to the best possible measurement on the probe. Okay? Now, so again, we have a Kramer-Rao relation here. Now, the uncertainty estimation of the parameter is bounded below by that expression, which depends on the quantum Fisher information of the system now. So for pure states, it is actually possible to calculate the quantum Fisher information if the probe has a unitary evolution, like you see in the second line of this slide, then you can show very easily, actually, that the quantum Fisher information is equal to 4 times the variance of an operator. And this operator is related to the unitary evolution of the probe. Now, in order to understand what that means, let's consider a simple case in which the unitary evolution is given by that expression there. It's the exponential of I times some operator times the parameter you want to estimate. Now, if the unitary evolution is given by that, then you can show that the parameter, that the operator H coincides with the operator O in that exponent. In other words, H in this case is the generator of the transformation, and then the Kramer-Rao expression becomes that one. The uncertainty estimation of the parameter is actually bounded below by basically the variance of the generator of the transformation. Okay, so that's a very general result. By the way, if X is time, okay, then H should be the Hamiltonian. That would be a unitary evolution. And the variance of the Hamiltonian is, you can find in the formula below. And delta X will be just the uncertainty in time. And so that means that the uncertainty time is 1 over square root of the variance of the energy. And that's a time-energy uncertainty relation without the need to introduce a time operator. Okay? So it comes out from the Kramer-Rao relation and not from the Heisenberg uncertainty relation. So that expression also shows that in order to get a better precision, you should increase the variance. Now, let me give an example. That's the uncertainty in the estimation of a phase in a Mach-Zehnder interferometer. In this case, the generator of phase displacement is the number operator, if you find that. And therefore, the quantum Fisher information is related to the variance of the number operator in the initial state of the system. Now, so for a coherent state, this variance is equal to the average number of photons. And then you find the equation you have that, the uncertainty estimation of the phase is bounded below by 1 over the square root of the average number of photons in the field. Now, can we do better than that? Yes, we can. We can increase the precision by maximizing the variance with so-called noon state. And the name is made clear from this expression. So it's a state which has maximal variance in the upper branch, either have n photons there or 0 photons there. And indeed, when you calculate the uncertainty in the phase for this state, you find that now the variance is limited below by 1 over n, which is the so-called Heisenberg limit. So for the same number of resources, you get a better result than by using coherent state. Okay? So that's how it works. And however, we have a problem here. You see, Noon states are very nice if you don't have loss. On the other hand, if you have a loss of a single photon, you transform immediately the Noon state into a separable state. Okay? So, and then you don't have phase information at all. So the loss of a single photon erases completely the information on the phase of the system. Now, while for noiseless systems, the quantum Fisher information is easy to calculate, and it's easy to know what kind of state you should use. For noisy systems, it's more difficult. This can be explicitly calculated for Gaussian states or low-dimensional systems. In general, we don't know how to do it. And that's why, some time ago, we developed a general framework for estimating the ultimate precision limit in noisy quantum-enhanced metrology. And the idea is a simple idea. If you have a system S, which is in contact with some environment, well, the system S is not pure, the evolution is not pure, the evolution of the probe is not going to be a pure evolution, but then you can consider the whole system, S plus E. You include the environment, and by doing that, you have now a unitary evolution of system plus environment. That's called purification of the system. And now if you can measure, apply measurements on S plus E, you should have more information about the parameter than if you just apply measurements on S alone. And this means that the quantum Fisher information for S plus E is an upper bound for the quantum Fisher information of the system. Now we have applied this to many systems. I'm not going to go into the details of that, but just let me give you a taste of what that means. Let's start with a very simple situation. We have an absorbing material, say at 0 temperature. Now, many people have remarked that this dumping material can be replaced by a beam splitter. And if you look at the beam splitter, now you have not only the outgoing mode and the incoming mode corresponding to the absorbing material, but you also have another mode, which is the vacuum going to the beam splitter. Now, of course, the beam splitter system has a unitary evolution, but we are interested only in mode A there, which is the outgoing fields. And it's easy to show that if you trace out mode B, so if you're only interested in mode A, you get the Master equation for the dumping material. We can also, by using this scheme, we can show that this upper bound is actually saturated. It's reached by Fock states. So Fock states are the best states to estimate this absorption coefficients. And furthermore, the best measurement is a photon count measurement. Okay? So that's a simple example. And a more complex example comes for the estimation not only of the absorption constant, but also of the temperature of the system. And then we can have, so this is look at me in a bad way, you know. So is that harassment? Or So suppose now the temperature is different from 0, then we can show, and that was shown in these 2 papers that you can see there, that you can actually replace the open system by a closed system, which now has not only the beam splitter that you see there, but also a squeezing system, an optical parametric amplifier that introduces another mode in the system. Now we have not only the original mode, but also mode B and mode C. And then if we trace out mode B and mode C, we get the Master equation, depending on the temperature for the dumping system. So we use that to find the quantum limit for the measurement of a classical force coupled to a noisy quantum mechanical oscillator. And we show there that this scheme here is actually saturated by an initial Gaussian state. Okay? And also, so that was done with my student, Latun. Escher was also a student, and Rui Matos Filho, a colleague of mine there in Rio de Janeiro. And then together with Jashuan Wang and Girish Agarwal, we did this other paper on estimating the dumping constant in temperature using this idea of unitarizing the system, okay? Considering the whole thing, including the environment. Now, before I have some aggression against me, I should tell you that you know, I have told you before that entanglement is fragile. So the null state will not work with the dump system. And in fact, we have studied that in our group. Experimentally, these are the 2 papers shown at the first part of the slide. And what happens if you have an entangled state, and that's shown in that picture there. Suppose you have an entangled state of 2 atoms, which can be both in the ground state or both in the excited state. Then if the population of the excited state is larger than the population of the ground state, something funny happens. That curve is the curve that shows the decrease of entanglement because you have some dumping in the system. And that's measured by the concurrence, but I'm not going to go into detail here. There's some measures of entanglement. And then you see, and P is the probability that of decay for each atom. So P equal to 1 means that the atom has decayed. And what you see there is that before the atoms have decayed, the entanglement can disappear. And in fact, we can show that after that point, coherence still lives, but entanglement is not there anymore. That means that entanglement is more fragile than coherence, which means, you know, that could be bad news for quantum computers, maybe. But these are very good news for quantum metrology, because if entanglement is so sensitive to the environment, it would be a very fantastic tool to measure the environment. And that's what I want to show in my last slide. I'm really afraid of the chair. So, for instance, you want to estimate absorption. And we want to avoid using Fox states. Okay? Fox states are the best states for estimating absorption, but come on, no? They are not easy to produce in a lab, especially if the number of photons is larger than 2 or 3. So what we propose is the following. This is a submitted paper. You can find it in the archives. Instead of using just one mode, we use two entangled modes. This is a two-mode squeeze state produced by an optical parametric amplifier. One of the modes goes through the system for which we want to estimate the damping or the scattering of light, and the other beam doesn't go through it. Now both get to this second optical parametric amplifier, which is the inverse of the first one. So that means that if you don't have a medium there, you start with a vacuum on the left-hand side, you end up with a vacuum on the right-hand side. So in some sense, the second optical parametric amplifier gives you a null situation if you don't have a damping. And then you measure, after the second OPA, the total number of photons. Okay? So this is based on this very simple expression for the squeezing state. You can show that if you have a squeeze state, it can be expressed in terms of correlated Fox states. And that's why we can replace the Fox state by this strategy. And in fact, we get for this precision the same value we would get for a Fox state. Okay? It's actually the average of the Fox states there. It's a very good result. And this is the final result I want to show you. The green curve corresponds to the classical estimation of absorption. Classical means you send a coherent state to the sample, and that's the precision you get. The red line corresponds to the precision obtained with the system I just described to you, and that works, we have shown, for small values of gamma. There is a reason for that. I'm not going to go into that now. And the value of delta gamma for the red line is shown there. You see that there's a gamma in front of the 1 minus gamma. So it's interesting because, you know, if gamma goes to 1, you remark that the red expression goes into the green expression, which is another example of the classical limit when you have strong dissipation. Okay? So the quantum curve should go into the classical one, but in other situations, for small gammas, there is an appreciable difference between the two estimations. For instance, for the number of incoming photons equal to 10, the gain in using this scheme, which is shown there, is of 5 decimals. Okay? So that's what I wanted to tell you. I just want to finish by showing you a map. That's a map of Brazil, and that shows the several institutions which are affiliated to the National Institute for Quantum Information, okay, which is associated to the federal government, the initiative of the Ministry of Science and Technology in the beginning of this century, actually, a little bit, 2004, something like that. And there are many places. All these institutes here, they have about 120 principal investigators, and of course, students and so forth. And I should tell you that due to this kind of initiative, places that did not have any lab were able to build the labs thanks to the money of this quantum institute. And now I'm a theoretician, I am vice director of this institute, but we make it a very important point that all the money should go to experiments. Nothing, no trips, not even no postdocs, theoretical postdocs, you know. The stress is I mean, we just stress the importance of experiments in this field. And with that, I finish my talk. Thank you very much for your attention.